Good morning, everyone. Thank you for joining our webinar today. Today, we're talking about kiln technology, what we know about improving production efficiencies. I'm Sylvia Herzog from the Charcoal Project. You hopefully have been to a couple of these presentations, which we are doing this year in order to highlight different ways to make charcoal and charcoal-related wood fuels more sustainable. We have a great lineup today. We have a great lineup today with Dan Sweeney, our partner from MIT D-Lab, as a moderator, and he's going to do a brief intro for you. We also have Kevin Kung from Takachar, who's going to talk about their technology and their work with biochar. And then we have Happy Amos from Roshan Global Services, who's in Nigeria, who's going to talk about their briquetting operation. And together with Dan Sweeney, they're going to do show you a little case study. Before we get into that, we're going to just a little housekeeping. Please keep your microphone muted and your camera off, just so everyone has a good connection. We are going to have a Q&A session at the very end. So if you have questions during a session, please just post them in the chat function and we'll answer questions that way. A recording of the presentation and the slides will be available in about a week or so afterwards. We'll clean everything up and then send it out to all of you who have registered. And then any questions that we didn't get to, we will make sure we address any questions that were in a chat. So we'll answer those in the follow-up material. Just so for those of you who don't know the Charcoal Project, though a lot of you do now, we are a US-based nonprofit, which we focuses on better fuels and technologies and policies for those who depend on charcoal and other solid biomass fuels. We do that by supporting clean energy entrepreneurs through our Harvest Fuel Initiative, which is a collaboration with MIT D-Lab. And we provide online resources to stakeholders in the sector. And we also advocate for more sustainable practices for wood fuel consumption. And this webinar series is an example of how we do that. So I'm very happy to have you here today. And with that, I'm going to turn it over to Dan. Sorry for my screen flipping around. Dan, I'll stop share and you can step in.
Sounds good. Great. Thanks so much, Sylvia. Nice to see everyone. Thanks for coming. And thanks to the Charcoal Project and Sylvia for having us today. So my name is Dan Sweeney, and I'll be the moderator for today's webinar. I'm a research scientist and lecturer and a mechanical engineer at MIT D-Lab. For about the past 8 years, I've been working with the Charcoal Project on a number of different charcoal briquette enterprise assistance programs, and mostly focused on research and development, working on manufacturing, and also on product testing. So it's really good to be here. I have a brief introduction that I'll show, and then we'll turn it over to our two speakers, Kevin and Happy, who are going to tell you a little bit more about their projects. For my introduction, we had a little bit of time, so Sylvia gave me about 10 minutes to just go through a few things. So let me just share a screen real quick. Great. So today we're talking about kilns, and this is something that I've been very interested in ever since I started working in the charcoal sector and the briquette sector. I know a lot of us are coming from different places. Maybe some of us are producers ourselves, or researchers, or working at NGOs or other organizations. So what I wanted to do was give a little bit of background just to kind of align all of us in terms of what we're talking about here and some common language. And then I'll talk a little bit about a few advances that have happened recently, and I'll let Kevin and Happy talk more about their own experiences. But usually this is what my kiln efficiency and performance talks look like. So I actually teach a class at MIT at D-Lab where every semester we go out and make charcoal. So this is us out on the campus, out at the Kresge lawn, just outside of a famous auditorium on the MIT campus. Kevin's been here before with me. And here we are, this is just a few months ago actually, where we're firing a drum kiln. And I'll talk a little bit more about what's going on here, but this is what I'm typically used to. So if it seems like I'm a little less comfortable on the the screen here. Someday I hope we can all join and fire a drum together and make some charcoal. But for now, here's what we want to do today. So again, I'll give a short background and some alignment. We're going to learn from Kevin and Happy about an interesting technology and a producer's experience with those. What I'm hoping is that we have a chance at the end to share and exchange respectfully, like Sylvia said, and also productively. I think I keep learning more about new carbonization and kiln technologies. It seems like every week there's somebody new who's getting in touch. So I think there's probably a lot that I still have to learn. And I think a lot of you have lots to share. So I hope we have a chance to do that here and then hopefully even after this webinar. And all of these things, we're working toward technologies that hopefully will meet the needs of producers and also users. So the products that we're making meet the needs of users in communities where we're working. Probably what we won't be able to do today is we definitely won't be promoting or picking winners. I'm sorry if you came here expecting that, but I think we have a lot of work to do on understanding what technologies are suitable for what purposes. We're going to learn about a couple today, but there's many that I'm not going to speak about that I think, hopefully we have a chance to talk about later. And unfortunately, I won't be able to go through a full history of kilns and carbonization. It's a long history all the way back to ancient times, and we don't have time for that today. So if your favorite kiln or something you worked on didn't make it into today's webinar, keep in touch and we'll hopefully talk about it in the future. So again, going back here, what we're focusing on here is the kiln itself. And so there's a few things I wanted to point out as we talk a little bit about some background on carbonization. So what the students and I did before this is we loaded this drum. Some of you will be familiar with drum kiln technology, others if not. The oil drum here is meant to contain the raw material. So in this case, we loaded this with sticks and twigs. We lit a small fire at the bottom. And then here's about maybe 15 or 20 minutes after that, at which point we had a big fireball emanating from the top of this. And about 30 minutes later, we closed up the kiln and came back after an hour to find out how much charcoal we had made. So what I want to talk a little bit about is actually in any kind of fire, we go through a process where charcoal is made, or char, sometimes we refer to it. So even in a common wood fire, there's a step where all of the gases come out of the wood and we're left with the carbon-rich residue, actually, which is called char. Now, if there's enough air, the char continues to burn, right? We see all this is red hot in the background. Char continues to burn and we're left with ashes at the end. So one of the purposes of our drum, which we call a kiln, is to limit the amount of air that goes into the fire. So we can even consider a simple matchstick as another case. So here there's a lot going on, but essentially as the wood heats up, the gases, or what we call the volatile matter, are released from the wood. And that's actually what we see as the visible flame. It's not the wood itself burning, but instead the volatile gases that are coming off it. And as those volatiles are removed, what's left is char. So I think a lot of you probably already know about this. And there's, within the flame itself, there's a lot of things happening. I'm not going to talk about that, but sorry about that. So within the process of carbonization, we can break that up into a number of different steps, right? So we start with our raw biomass. In this case, we see some wood chips. Now, as we progressively heat that up, and especially heating it in an environment where we have very little air, right? Unlike our wood fire, our campfire, we don't want everything to end up as ash. We want to be left with this carbon-rich charcoal residue. So as this progresses, we go through a number of different processes. The first one, up to 100 C, is drying. And then as the biomass continues to heat up, 200 to 300 to 400 C, there's a few different things happening. So finally, we go through what a lot of us call carbonization, which is at a slightly higher temperature. But before that is something maybe you've heard of, torrefaction. So in this case, it's a slightly lower temperature kind of like a light roast on your coffee beans, if that's an example to consider. So torrefaction, carbonization, the temperature continues to rise more. We have high temperature carbonization. And then usually in most cases, I think most of the applications that I've worked in, that's sort of where we stop things. So maybe our kiln reaches 500 or 600 C. All of those volatiles that were in the original wood chips or biomass have been driven off, and we're left with our char. There's a couple other steps. We could take this further and produce something maybe a little bit higher value or used for different purposes. Coke is often used for metallurgy, a fuel in smelting and processing of metals. And then activated charcoal is another product. We can produce that after carbonizing by introducing the charcoal to a steam environment. So those are different. We won't talk much about those today, but there are a bunch of different things we can do with charcoal. Now, one of the things I wanted to point out on background here, so this is a little bit of a complicated graph, but there's a really important dependence of what we end up with in the end of carbonization on the temperature that it reaches and how much time that we have. So what we have here is time on the x-axis and temperature on one of our y-axes, and then what we call mass loss on the other y-axis. So if we consider our original biomass here at the top, we have 100% of that. Let's say we have 1 kilogram of biomass. Now, as we heat that, we said first we go through drying, right, up to around 100 degrees C. So our red line shows the temperature. And right there, for a lot of biomass, we lose a lot of the mass just through drying itself. So for this example, we actually lost almost 50% of our mass just as water. Now, as we go through these other processes, torrefaction and carbonization, now we start to lose those volatile materials, right? So in the end, we may be left with 40% or less of the original mass of our fuel, right? So when we saw the flame at the top of the drum kiln, that was all of our volatile matter that had been driven off and was flaring and burning above the kiln. So this is actually really important because we use this mass loss as an indicator of the performance of the kiln. So we're going to talk about one of those measures that we use for kiln performance, and that's char yield. So I think probably a lot of you are familiar with this, but for those who aren't, the yield of the char is the ratio of the char produced to the initial feedstock mass. So we have a simple equation for that. And Happy and I are going to show some actual results from some experiments, but the char mass divided by the feedstock mass. So we know that this should end up being a number less than 1. And just as an example, we did some experiments with our drum kiln some years ago. I think this was using sugarcane bagasse, where we loaded the kiln with 31 kilograms, the original feedstock mass. We were left with about 8.5 kilograms. So we considered that a 27.4% yield of char. So that's a pretty important number. Maybe a lot of you have heard traditional forms of charcoal making can be relatively inefficient. And even actually, if you don't really know how to use a more modern form of kiln or a drum kiln, you can also have fairly low efficiencies in terms of char yield. So that's a fairly important number, but unfortunately, it doesn't tell us a lot about the product or the quality of the char that we've produced. So for some of our applications, if it's biochar for fertilizer or char to make fuel briquettes, the quality of that char product is pretty important. So another few measures that we could consider in terms of performance, we have energy efficiency. This actually isn't that commonly used, but if you were concerned about how much energy is preserved in your char compared to the original feedstock, this is an equation for that. Typically, it's less than 50%. So the char that we've produced will have 50% or less of the energy that was in the original feedstock, if we consider it as a bulk, right? So, but on a per mass basis, char often has a much higher energy content. And then I think there's a lot of other considerations that we should consider when it comes to performance that maybe don't show up in these equations that we use, like capital cost and operating cost, the skill required to operate a kiln. Is it portable? Could we move it to a place where they have a lot of feedstock, for example? Can it operate on different feedstocks? What's the quality of the product, and how much tolerance do we have from that for our final product? Another thing is the service and maintenance requirements for the kiln and the capacity. We don't want something that's very highly oversized compared to the availability of our feedstock. So this is a short list. I know there's many others, and we can talk about those later. So one of the important measures, especially for fuel briquettes, is what I call the fixed carbon content. And this is commonly an indicator for the quality of charcoal, especially if you're considering it for a fuel use. And on this graph, we're showing fixed carbon, which is our upper curve, and the lower curve is the yield, the actual yield of char. So the interesting thing here for a lot of kilns, there's actually a strong dependency of fixed carbon on the temperature. So kind of like we saw in that other graph, in the end, we'll just be left with carbon or fixed carbon. So that fraction of the final product goes higher and higher as the temperature goes higher. So you could say we have a higher quality product with a higher temperature, kiln operating temperature. Now the downside here, or the trade-off, is that the fixed carbon content in our final fuel, our final material that we produced, is inversely proportional to the yield, right? So we have to remove a lot of other material, right, which causes our yield to decrease in order for our fixed carbon content to increase. So for those of us that especially are making fuel briquettes, this becomes important as we're trying to make a fuel that somewhat closely behaves like wood charcoal, which would be the conventional fuel. So that's one of many trade-offs. I just wanted to highlight that one. So then I'm going to just speak briefly about a few advances that I've seen in the sector just before we get to Kevin and Happy. So one thing I've noticed is that there's a big need for making char from fine biomass. A lot of kiln technologies in the past were made for wood. And we found that there's a lot of other feedstocks that can work well for making char. I know both Kevin and Happy are utilizing other materials besides wood. And so a couple of examples I think that have helped advance that. We may not call these very advanced in appearance maybe, but they're important nonetheless. And so one of those is the ability to carbonize rice husks and other very small, very fine feedstocks. So here we have a picture of a small scale mound carbonizer. So on the inside, we would start a small fire and then basically heap rice husks or other fine biomass around that. I know some people have also experimented with things like groundnut shells and macadamia nut shells with a similar type of kiln here. And then another example, many people are now utilizing sugarcane and different fibrous biomass, which can also be fine in size. And so this is an example. This is a T-Lud carbonizer from a group in Kenya. T-Lud meaning top lit updraft. So these would be batch loaded with bagasse or other material lit from the top, and then slowly that carbonization front travels down. So those are a couple of examples. Another interesting advance is the ability to utilize the volatile gases. So you remember in the beginning, I showed that kiln, the drum kiln with the fire emanating from the top of it. So there's a couple kind of more advanced ways to utilize the heat from that fire. So one of those is called a retort kiln. And what this does is it burns the volatile gases to actually supply heat back to the feedstock in the kiln. So hopefully some of you are familiar with this. Happy is going to speak about her experience using one of these. But this is important because we know that we need some heat to drive pyrolysis, carbonization, torrefaction. Most of these require heat. And so in most cases for traditional kilns and unimproved kilns, that heat is supplied by sacrificing a little bit of our raw material, combusting that all the way to ash to provide heat to carbonize the rest. Another clever example of this, I think, is capturing the heat from the gases. So rather than maybe supplying that back into the kiln, this is an example from Cambodia where this factory actually has a hood system and a capture system where the heat is then routed into a tunnel where they use that heat, in this case for drying briquettes. But you could imagine utilizing the heat for a variety of different tasks. And then finally, a thing I hope that we can work on more moving forward is the continuous production of char. Most of the examples that I've showed so far are what we call batch production. So we load a batch, we fire that produced char, wait for that to cool, remove the char, and then start again. Or maybe we'll operate multiple kilns in parallel. Continuous, on the other hand, means that we're actually continuously feeding in feedstock at the same time that we're removing char from the outlet of the kiln. So there's a couple of examples of this that probably some of you have seen. There's one which utilizes a mechanism called downdraft gasification. So this is a kiln made by a company called Husk. Actually don't think they're making them anymore, but I actually had found when I visited a few places using this that while they are meant to produce gas, which can be used to produce electricity or heat, if you run it in a different way, you can actually produce quite a lot of char. So in this case, maize cobs or other biomass, rice husks are fed through the top and char exits through the bottom. Another example that we have seen just starting to gain some use, there's a group in Haiti that had been using this type. It's called a Rotary Hearth kiln. And in this case, biomass is fed in and then sort of falls through a cascade of different chambers. So starting with lower temperature up to high temperature. And char exits out the bottom chamber. So these are a little more complicated and maybe a bit more costly, but they have some advantages in terms of flexibility and efficiency, and the ability to run continuously. So just as kind of an overview, we kind of brushed on a lot of these in the past 10 minutes, but in order to work on improvements to performance of our kilns, here's a few things to consider. So one is understanding what our target product is and actually matching production method to that. If we don't need a very high fixed carbon content, we don't need it to be a super high quality char in terms of use for combustion, and we're trying to reduce the emissions, maybe we don't need to have a very advanced method for carbonizing. The feedstock preparation is also important. So probably one of the easiest things we can do to improve performance is by drying the feedstock in advance. Just the removal of water and moisture in the feedstock in the beginning ends up being a huge energy sink. And so removing that before putting the feedstock into the kiln can really help performance. In some cases, size reduction will also help. Smaller feedstock tends to carbonize faster, but there's a trade-off where we need to maintain airflow through the kiln. Utilizing the volatile gases, so burning those and capturing the heat, either to carbonize more feedstock or to have process heat for something else. And also minimizing the uncontrolled infiltration of air. A lot of more basic kilns that I've seen, including a lot of the drum kilns that I've worked on, we don't really have a great sense of the proper amount of air to be introduced into the kiln. So I think also as kilns degrade, we end up getting pathways for other uncontrolled infiltration. So just keeping track of those is important. Insulating can also be very helpful. The drum kilns that I've worked with are not well insulated at all. And therefore we lose a lot of the heat that we're producing, which could be used to drive those carbonization reactions. So just adding a bit of insulation or using say an insulating fire brick to construct the kiln. Regular inspection and maintenance, I think that's pretty obvious. And then finally, what I've found is just experimenting and practicing. So if you're interested in trying a new feedstock, or you're not sure how well your kiln is working, utilize those performance measures that we have and practice with those things. I think a lot of us are doing that probably. So at this point, I'm going to wrap up. We're going to take questions finally in the end, so please save those. First, we're going to hear from Kevin, and he's going to talk about his small scale and low cost portable biomass upgrading equipment that he's developed. Then next, I will turn it over to Happy. So for now, I'm going to hand it over to you, Kevin. Thanks.
Yeah, thank you so much, Dan. Can you hear me?
Yes, I can hear you.
Great. So I'm going to share some slides. And just by way of introduction, I am co-founder and CTO of a company called Takachar, but previously a student at MIT who also worked with Dan on some of the earlier kind of kiln processes. So honored and excited to be here to share what our experience has been and also to learn from all of you. So maybe I will just start by giving an overview of Takachar's work, and then talk about some of the experiences we have, both with the mount kilns as well as some with the later development that we made. So for Takachar, our mission is to increase the amount of crop and forest residues known as biomass economically converted into useful products. And more than 4 billion tons of it is being burned worldwide, which is not only an economic waste, but also is significant pollution. So one of the problems with handling biomass in a centralized way is that it's often very loose, wet, and bulky, which means that it costs tremendously to move it from place to place. And that cost often shuts out many rural communities from accessing and harnessing that as a source of value. So we develop small-scale, low-cost portable systems that can latch onto the back of tractors and even donkey carts, and that can be deployed to single farms as well as logging landings to convert with no external energy input local residues into higher value bioproducts and biofuels. And these are some of the examples of the prototype that we built initially at MIT and then later in the field. And what we could do is that instead of centralizing the processing of biomass residues, what we could do is have this decentralized process in the local communities. And in many cases, having a local use, either as fuel or fertilizer or other types of chemicals. And even in cases where the local community doesn't have a use, then moving that to a centralized place normally will save about 30 to 70% of transportation costs through this decentralized kind of pretreatment approach. So what are some of the output products that our technology could produce? So it's a thermochemical conversion process. So solid fuel charcoal is one of them. We also have had experience making biochar fertilizer, and I will also speak actually a case study of doing that and our experience there. This could also make chemicals, and in some cases as a waste management. So it's a customizable process that, depending on how you ramp up the temperature and residence time, give you different types of products that you can craft to different end users' requirements. So our story actually started in Kenya back in 2013 when we had this lot of kind of rice husks nearby that's being burnt in the open, right? So the initial idea was to say, can we actually carbonize this rice husks into something that's like either a fuel briquette or other types of kind of biochar-based fertilizer? So our initial experience actually was with mount kilns. So as Dan was saying, right, I mean, this is a way that an open source way, I mean, it's $20, doesn't cost that much to make. And after a few hours, we get this char that's then processed. So once we had that, we decided in this case to focus on agriculture instead of fuel because of given the high ash content of the rice husks, which makes it relatively challenging to burn as a fuel. So we made it into a mineral-rich biochar-based fertilizer blend that help rural farmers till integrated land reverse their soil acidity and degradation. And a lot of that is because of this biochar-based formulation can result in improved nutrient and water retention, at the same time sequester carbon back into the soil, therefore decreasing the amount of soil carbon in a lot of degraded farms. And so this is sort of how the process looks like, right? I mean, lighting the kiln first and then piling that with rice husks. And for batch, you can get about 50 kg of the char. We mix it with recipes for making nutrients complete and then package them and eventually selling them to the farmers directly. And this is in partnership in Kenya with a company called Savvy Organics who does most of those local operations. Yeah, and let's hear from some of what the farmers have to say. So over the past few years, we were actually able to expand to about 5,000 farmers in the Kirinyaga County. So if any one of you is located in East Africa and want to head up that way towards Mount Kenya, we definitely can show you the production site as well as sort of the mount kilns that many of which are still in operation at our facility today. But through this process, what we found was that this carbonization process, which we used, was a bit limiting. Right. Number one is that as we go to scale to sort of 1 to 2 tons per day, we needed to deploy maybe 10 or 20 of those in parallel, right? Which is pretty labor intensive and land intensive. And a lot of the cases, we end up having a lot of this, uncontrolled kind of volatile emissions, which is undesirable, right, at a larger scale. So those were the starting points and also limitations of the kind of the open source mount kiln technologies that really inspired me to start working on more kind of continuous, high throughput, and kind of clean emitting kind of process for doing the same thing. So at that time at MIT, I started my work on, it's partially inspired by these kind of open drum kilns, right? The idea is that we inject air at the bottom to react with biomass in a limited combustion region, right? In this case, biomass comes in as a moving bed, so it's driven down by gravity, right? And we attach a motor drive and a screw auger to it so that it continuously removes the output product after it's completed, right? And then the heated flue gas after combustion zone, it flows countercurrent upwards from the biomass, and it also heats up the incoming biomass. So a normal kind of temperature profile, this approximate temperature profile will look something like that, right? Where you start at room temperature, and as you come down, you eventually get to a carbonization regime. And what we did find was that with this, we can also control the reaction, right? So by altering the amount of air with respect to biomass, you can control the temperature. And by altering the motor drive speed, you could control how long the biomass spends in there for the residence time. So for us, those are the ways which we could use to tune the reaction to have the customizable outputs that end users require. So here are some of the prototypes we've built: a NanoTorque V2 version 2. So this is at MIT with a very small kind of lab toy, I guess. And then subsequently we scaled that up to a MicroTorque, which is a kind of pre-commercial prototype. And from there, we were able to validate this across many different types of biomass using the same equipment, ranging from rice husks to almond shells, wood chips, coconut shells, and pine shavings and hay straw. Right? So those are things which we were able to test and char under different conditions and different input kind of variabilities. So what are some of the performance metrics that I think we can quantify those in accordance to what Dan just discussed? One is the char yield, right? And that's, obviously depends on the reactor configuration. So on the x-axis, I'm plotting how long the reaction is happening. The solid spends on the y-axis, how much air we are feeding in compared to the biomass. And we can see that the output yield and the reaction condition changes as a result of the condition. But normally we get something anywhere from 35% to 75% in terms of the mass yield, depending on the reaction severity. We could also define the same for energy yield, which in Dan's slide is efficiency, which energy of char out versus the energy of biomass in, and ranges. It differs from feedstock to feedstock, but normally from 40 to 80% in our experimental prototype. And the quality of the char, we actually did not define this as a fixed carbon, but a related parameter that we called energy densification ratio, which has relevance in cooking fuel because it's directly related to the higher heating value of the char coming out versus the higher heating value of the input biomass. And as we can see that we can tune, as we go up in the air, fuel ratio, we increase the temperature and we get a purer kind of denser form of carbon that's higher in energy density. But the trade-off is that you get lower mass and energy yield, right? So those are things which demonstrate that the technology is able to customize to different output fuel and bioproduct requirements. So where are we now? We are actually in the field. So this is a prototype which we built in outside of New Delhi in India. And we are slated to build a second prototype, sort of a commercial scale kind of level at our site in Kenya, in the Kirinyaga County. And a lot of those units are also portable, which means if it tests successfully in one place, we could also move it to elsewhere. So be very much interested in just learning sort of what other test sites and potential partners that we could also learn from and really test the equipment in the next year or two. Yeah, so with that, I will close. If you have any questions, feel free to email me either at kevin@takachar.com or trashiscash@mit.edu. Thank you.
Great. Thank you so much, Kevin. Really good presentation, and thanks for sharing those two approaches. I forgot about the mound kiln. I mentioned that in my presentation too, but I'd forgotten you guys had started there and have come a long way since that. So we will have a chance to take questions for Kevin after our next presentation. So with that, I'm going to introduce Happy Amos, who is a charcoal briquette producer and has quite a lot of experience now using different kiln technologies. And she's going to share a little bit about her company in Nigeria and also some experience that actually she and I had working with one of her kilns. So Happy, are you there?
Hello, everyone. Can you hear me?
Yeah. Thank you. You can go ahead.
All right. Okay.
Happy, unfortunately, I think you accidentally muted yourself. Can you unmute?
Oh, okay. Sorry about that. Can you hear me now?
Yes, we can hear you well now. Thank you.
All right. Thank you. So Roshan Renewables, we are into providing friendly, clean cooking and home lighting products to basically improve the standards of people. And previously, we just do cook stoves. We manufacture the biomass fuel efficient cook stoves because we have a population of about 70% of the Nigerian population depending on inefficient cook stoves and fuel for cooking and heating. And we've had reported cases of high risks and drudgery from fuel wood collection, environmental degradation from excessive tree cutting. And according to FAO, just between 1990 to 2010, Nigeria lost about 47.5% of its forest cover. And we have about, according to World Health Organization, 95,000 people die annually from indoor air pollution. So we have a range of products that we work with in Roshan. We have our Happy Energy Saving Cook Stoves, as you can see in the pictures. And we have the briquettes we are manufacturing. We also do consultancy service by offering training services on small groups of people making their own briquettes within the communities. And we also have institutional cook stove for rice parboiling, where women use it to process paddy rice. So we fell into the briquette project when, as a Roshan, we saw it as an opportunity to have a product that will bring the customers back to our doorsteps daily. Initially, when we sell the cook stove, which has about 2 to 3 to 4 years lifespan, we do not have customers coming back within that period. So in the bid to increase our cash flow and to also have returning customers, and also the need for briquettes based on the statistics we were seeing on the loss of the forest cover, we decided to go into the briquette production. And the most available feedstock available for us are the palm kernel bark from the palm fruits, the sawdust from wood mills, then from rice husks, we have also bamboo, waste bamboo. We have a lot of building sites since Nigeria is a developing country, and especially the area where I come from, which is about the central, there are a lot of building sites coming, and bamboo, a lot of bamboo is being used, and after the building is just being thrown away. So we have that a lot. Then we also have the corn husk, and also the sesame stalk, which we later discovered, interestingly, makes a good feedstock for briquette. We were using the drum kiln to carbonize, but it was in small quantity. It didn't give us the opportunity to carbonize in large quantities. So we needed to have like several drums lined up to be able to increase our output. So, but I wasn't comfortable about having to have several drums lined up because I have issue with space, and also in the bit of research to know if there are other options for carbonizing, we came across the Adam Retort. So upon coming across Adam Retort, we realized that we needed to buy a license to build it. It's not the design and all that we need to build. It was not readily available for free. And then it had the caveat about the international organizations like UNDP project or something cannot have access to the license. It has to be private individuals or private organizations like Roshan. So we now had to start looking for funds to buy the license, which is not so expensive, but it will have helped for small scale business for us to have had it a lot lesser. We got the license, and then, but the sourcing of the materials, the equipment was quite easy because they were already available for us within our area. We built the kiln in about a week, and we allowed it to dry before we started firing it. So we found we could use the same feedstock we used for the briquette to fire the kiln. So there was no need getting firewood to fire the kiln, which was very good for us because that will reduce the cost of production. Because another thing for us as business is that we have to keep the price of charcoal briquette at par with the price of the firewood charcoal that is being produced locally. Then another experience we had was the smoke from the retort was a little too much, maybe because our chimney was a low, and so our neighbors complained that the smoke was going into their houses, their space. So we had to extend the chimney, but after extending the chimney, the complaint reduced. Then it solved the issue of quantity for us because we could fire a large quantity per time. And we found a way to offload it and then reload it immediately so we do not lose energy. So, and thereby it further reduced the quantity of fuel we will use in reheating. But then because of our constant usage and the high temperature we keep generating, the metal began to welt from too much heating. And now we have to change all the metal components, most of the metal components to a higher gauge than the one that was specified during in the technical specification. So far our experience is more positive, but apart from the metal welting, which will cost us more repairs. So these are just pictures of the process. In the first picture, it's me and my team drawing out the floor plan for the kiln. Then it's me holding the pumice we use for insulation. Then this is the inside of the Adam Retort kiln. This is where you load, and the last picture showed this thing. So this is our staff loading the kiln with bamboo, the end char. And as I said earlier, the materials were easy to get. So these are some of the burnt bricks we use. And the picture here in the middle shows how the metal has welted from too much heat, and now the kiln has to go to an overhaul repair system. So, okay, I'm trying to get our Char Yield experiment. Okay, so this is us weighing before carbonizing. When Dan contacted us to know if initially we didn't weigh, but Dan contacted us and said if we could keep weighing so that we can get the yield. So we placed all weighed feedstock is placed in the kiln and fired, and the char produced is dried and weighed. So this is. Oh, sorry, did you lose me?
Yeah, Happy, we lost your slides. Can you bring them back?
Okay.
That's okay.
So where did you lose me from?
It was just, you showed us the pictures from the experiments, and then I think there was like just the results from the experiments that we're about to show.
Okay. So so the preliminary result, the feedstock mass was 253.2 kg. The char weight mass was 115.5 kg. Then after it was dried, we have 101.3 kg. Then the char yield is 40%, which we do not account for the moisture. We do not have the means to account for the moisture in the feedstock. So that is it for our experience with the Adam Retort kiln, and it's interesting to see the other technologies available, and I'm open to answer your questions. Thank you very much.
Great, thank you so much, Happy. Yeah, that was a great story, and thanks for sharing your experiments, and thanks for participating in those. Happy and I got in touch a couple of months ago about doing these experiments, and I thought it would be a nice thing to be able to present here today. So thank you so much and your team for actually doing those. So that's the end of our presentations. We're going to open up things now for discussion and questions. If you have any questions, you can put those into the chat, and I'm going to be fielding those as we go along here. We've had several questions for Kevin regarding biochar. I don't know if you've addressed those, Kevin, or is there anything else you wanted to add just to the whole group here?
Yeah, thank you. So I think in my presentation, I wasn't clear about the distinction between biochar and fertilizer, right? So biochar itself is not a fertilizer, but a soil amendment. So thanks the audience for pointing that out. And the way it works in Kenya is that we actually develop our own formulation as fertilizer chemicals or inorganic or organic components that we add back to the biochar mix. And we sell farmers sort of the complete kind of standalone fertilizer. So that can actually completely replace the traditional kind of chemical fertilizers, and the product itself that we have is actually certified by the government of Kenya as a kind of a standalone fertilizer.
Great, thanks for clarifying that, Kevin. You had another question about next steps for the prototype and the pilot demonstration. Did you want to take that here also?
Sure. So for us, I mean, right now we are actually testing our goal is to test the hardware as a robust, as different sets of conditions and agricultural contexts as possible, primarily in India as well as in East Africa. So if there are local kind of briquette producers or biochar makers or charcoal makers who are interested in working, definitely happy to be in touch with you and and see whether this is something that we can also test and demonstrate.
And then someone asked, Kevin, if you have an estimate on the yield from your most recent prototype. Do you have that, or can you share it?
Yeah, the yield itself depends on the kind of the reaction condition that we tune it to. The highest yield we're able to get is 75%, but that's under very light kind of torrefaction conditions where you are not driving out a lot of the low energy molecules. Under more kind of charcoal-like conditions, the yield will be similar to what you will get, which is around 30 to 40% by mass. And in terms of energy, probably around, up to twice as better compared to kind of open source kind of free venting kilns. In terms of that, because we can actually capture that heat and reuse it.
Great, thanks. So just to clarify, Kevin, your kiln does have a means for capturing heat from the volatile gases. Yeah, is that right?
Yeah.
Okay. Good. And then do you want to take this one, Kevin, at all? Did you consider trapping the smoke for wood vinegar production? I think that's from Teddy.
Good question. Delve that deeply into the liquid part. Most of us is focused on the solid part, and we sort of just oxidize, which means we burn that any volatiles mostly for energy. Wood vinegar potentially later on, but that hasn't been our focus in the past or present.
Yeah, and I guess also for me, Teddy, we haven't really worked much on wood vinegar production. At one point, we had done some experiments using your approach with a metallic pipe kind of attached to the outlet of the drum kiln. I don't know that much about optimizing for wood vinegar production, but I know you would want to basically operate the kiln at a relatively lower temperature. And I think if I remember right, a slower heating rate. So temperature is important. We didn't really talk about the rate that the biomass is heated, but I believe lower rate of heating would lead to more condensable and vapor liquid production. So that's just my experience. If you wanted to add something there, Teddy, feel free to unmute if you're able to. Great. Maybe we can do a couple questions for Happy. Are you still there, Happy?
Yeah, Dan, there's a couple questions about the type of biomass you guys Happy tested and what she's currently using, and maybe she could describe that a bit.
You want to talk about your biomass, Happy?
Hello, are you asking me? I
Yes.
can't hear you.
Yeah. So you had a question about what was the biomass that you used during the tests, and then have you tried any other types of biomass feedstock in the retort kiln?
Yes, so we've tried firewood, we've tried palm kernel bark, and the one that we have the results for, which is the one we weighed, is the bamboo. So unfortunately, we weren't measuring and taking all those into consideration until after our conversation with Dan. And so by then we just did for the bamboo.
Great. And then did you say, Happy, you're using some other feedstocks though in regular production outside of the experiments?
Yes, yes, we use palm kernel bark, we use corn husk whenever it's in season, and then we use the bamboo.
Great. You had a question about the bamboo. What are the challenges of using bamboo as a feedstock? Do you have any comments on that within the kiln or maybe even outside of carbonization?
So the only outside of carbonization, the only challenge we have is the constant supply for it. So because we always will have to wait until it's a waste material from the building site before we get it. So we do not have maybe let's say a farm that will give us a constant supply for it. And there is no other challenge we have with bamboo. We find it easy to carbonize. It takes less time than the palm kernel to carbonize, and it's easier to crush. So it's that's our experience with bamboo.
Great, thank you, Happy. And then did you also want to just speak briefly about your bamboo? I know it's a little bit off topic from carbonization, but your bamboo growing operation, I think that was interesting. You mentioned that to me recently.
Okay.
Yeah.
So for bamboo growing, we at this stage we are still just asking questions. However, we got a permit from the government to give that offered us about 10 hectares of land to grow, to have a woodlot where it would be like a source of feedstock. So, but we are still researching. We want to use indigenous trees, but we also want to use fast growing ones that will give us feedstock in a shorter period of time. And so we are researching if bamboo could be an option of what we could use that land for. So, but we do not have all the answers at the moment, but we hope that with further deliberations, we'll be able to come up with the answers. But we have the land, we have about 10 hectares approved for that.
Very nice, thank you. Someone asked about the license and obtaining the license for the Adam Retort. Happy, do you want to talk about that? What was the cost and how was that experience?
Okay, so getting the license was not difficult because I just sent a mail to Dr. Adam, who responded promptly. And but what I find difficult is that for each Adam Retort I have to build, I have to get a license for. So I cannot get a license to build one and then replicate over and over again. For each one I have to build, I have to get a license for, which I find a little difficult to deal with. So initially when we were buying, we had to get the license for about 8 of the Adam Retort. So the 8 of them cost us 930 euros.
Okay, thank you, Happy. Jackson has asked about using retort kilns to carbonize large pieces of wood. Did you ever try this, Happy? And did you have any challenges with that? Yeah.
I think Happy froze.
Oops, I think, yeah, we froze up. Okay.
Maybe while she's getting your connection back, Dan, there is a question there, just in general, a general question about best feedstock for briquettes. Maybe that's a good one for you to handle.
Yeah.
So it's easier to carbonize smaller woods with the Adam Retort than to carbonize the larger quantity for larger sizes of the wood. So when we tried the first one, it didn't carbonize right.
Okay, looks like maybe Happy came in and then out. I don't know, do you have any comments on that, Kevin? I guess you haven't done much with wood.
Yeah,
I'm back.
Yes, I mean, it can work. I think ultimately, as long as the average particle size is less than maybe 1/10 of the diameter of the equipment, it will work. So if you have something that's big, like twigs or branches, it becomes a bit more challenging. Yeah.
So,
Great, thanks.
hello, so I'm back. So I was saying, I
Okay.
don't know the last thing you heard, but I said that we actually have experienced some challenges carbonizing the bigger chunks of wood with the Adam Retort. So we find it's usually easier to have them into smaller chunks to be able to carbonize. So in the light of that, we stopped trying to carbonize the large sizes of wood and we just use the smaller ones. But now we completely stopped carbonizing wood and we are just using the waste.
Great, we got that. Thank you, Happy. Good. So I guess regarding the feedstocks for charcoal briquettes for fuel, I think, yeah, there's a lot of different feedstocks that can work. We've experimented with quite a few, and I know there's a lot of producers, many of you on this call, who are using different feedstocks. I think my general rule of thumb, you can find a lot of information online about feedstocks. And in general, I think if you can minimize the ash content and maximize the fixed carbon content, and if you're curious about what that means, I can share in the chat here. I have a couple videos actually that we've worked on, which talk about those things in a little bit more detail. I know, there's some very good high quality briquettes that are made from peanut or groundnut shells, coconut shells. Both of those have pretty high fixed carbon content. Obviously wood and wood residues. I know rice husks and grasses, leaves, those kind of things tend to have a lot of ash and very little fixed carbon. So they don't make the best as a fuel, but they can work very well for other applications like biochar. So anything else you would add to that, Happy or Kevin, your experience?
Yeah, hello.
Yeah, go ahead, Kevin.
Yeah, so from our experience, it depends. I mean, the different types of, it also depends on the type of feedstock and how their indigenous kind of qualities are, right? In Kenya, our anecdote is that we started trying to make briquettes, fuel briquettes from rice husks, which are not suitable because of the high ash content. And that's why we sort of assigned that to kind of more of a kind of mineral-rich fertilizer mix kind of purpose, right? But for other types of feedstock that our partners have worked with, like coconut shells, palm kernel shells, for example, those have been made into briquettes. There are different chemical kind of transformation that happens between different types of feedstock, but that's an area sometimes we are still actively working on understanding.
Thanks, Kevin. And Happy, do you want to add anything on feedstocks for briquettes?
So,
your experience?
What I would like to add is, so I find that in making good quality briquette, using only one type of feedstock does not give you the best result, especially if you're using it for fuel, especially for cooking fuel. And you have to use more of the one with the less, so I'm not so technical, but more of the one with less ash content. And I usually use the rice husks, which has high ash content, just for volume, not for quality, because the high ash content reduces the calorific value of the fuel. So with my experience, the ones with the higher calorific value mixed together with the lower calorific value for volume actually gives a better result than using just one type of feedstock over time.
Great, thank you, Happy. And I think you are very technical. You're using some terms that are quite technical. So again, if anyone needs more information on that, I'll put a link up in the chat about calorific value and fixed carbon and ash content. So I think we had another question on binder. And again, we're trying to keep focused here more on the kiln and carbonization. So regarding the specifics of briquetting and fuels and binders, maybe we won't go into a whole lot of detail on that. Do you want to speak briefly on the binder of choice for you, Happy? If you can share that.
Okay, yes, I can. So for me, I have two binders of choice. One is cassava starch, and the other one is gum arabic. I don't know if you know gum arabic. You know gum arabic, sorry, gum arabic from Senegal, Acacia. But gum arabic from Senegal, Acacia tends to be more expensive than the cassava starch. So we mostly use the cassava starch for it, and it works just fine.
Thank you. Great. There was a question from Jean-Francois on advice for a low-cost adaptable kiln to be used with palm kernel shells. I actually don't have any experience with palm kernel shells. I don't know if Happy or Kevin, either of you do.
Yeah, one of our partner does. So yeah, I just put the response in the chat and an email, just send it to me. I can put you in touch.
We also use the Adam Retort in carbonizing the palm kernel. It just takes longer than the bamboo to carbonize, but it works just fine. It's the first kiln I successfully carbonized the palm kernel back in, actually. Because of how hard the palm kernel back is, it was very difficult to carbonize it in the drum kilns. So, but it works just fine in the Adam Retort.
Okay, and you were saying, Happy, that it was difficult. It's very hard, so it didn't carbonize fully in the drum kiln?
Yes,
right?
It didn't carbonize fully. It took so much time. We lost some patience and all. So, and because we're business people, we want to find the most cost-effective, time-efficient procedures to get work done. So it didn't work. But with the Adam Retort, it worked just fine. And we are excited about that because we have a group of women who process the palm kernel nuts. So they have a lot of the back and they have nothing to do with it. And so they keep bringing it to the factory for us, which makes the feedstock quite accessible for us.
Okay, good. And just maybe one quick follow-up from me, Happy. How do you know, what's your method for testing if it's carbonized fully? I don't think we talked about that yet.
Oh, so I have to break it.
Yeah.
So that's just the easiest way for me is we break it. The easier it is broken into two pieces, then it's well, and then it's carbonized right through, all black. Then of course it's carbonized. But when it's hard to break and it won't, it's the inside is still hard and colored, then it's not carbonized. In my lame person's experience.
Good. No, that's the same way I do it. So yeah. We had a question from Sarah Basamara in Uganda. She was asking about time with the Adam Retort. Can you speak a little bit about that, Happy? Maybe for the different feedstocks that you've tried, do you notice that there's a difference in the amount of time it takes to carbonize?
Okay, so like I actually mentioned earlier that we carbonize faster with the bamboo than it is with the palm kernel, than it is with the firewood when we were trying all. So bamboo carbonizes faster. It takes a little longer to do with the palm kernel and takes a little longer to to work with the firewood. I wish I have all the time taken. Unfortunately, I don't have that data to share accurately with you.
Okay, but would you say it's like on the order of hours, like maybe 4 or 5 hours or longer than that?
So it will for palm kernel and firewood, it will take up to 5 hours.
Okay.
But with bamboo, 3 hours, you're done.
Yes.
2 hours, you're done. Yes.
Okay, good. And then actually from Dr. Chris of the Adam Retort designer, he was wondering how much can you fill? Do you know that in terms of palm kernel when you load that in the kiln? And no worries if that's too specific and detailed, you don't recall that. Happy, are you there?
Happy, you're muted again.
Sorry, my network is a little bad, so I'm struggling to hear. Keeps breaking.
There was just one question about the amount of palm kernel you can fill in the Adam Retort.
So we have them in about 50 kg bags, and we can use up to 550 kg to 650 kg per time.
Okay, thanks.
And I think Dr. Chris is here.
Yeah. Do you want to say something more?
He wrote in the chat box.
Yeah. Dr. Chris, do you want to add anything here? If you're able to.
Hello, you hear me? Everybody hears me?
Yes.
Yes, I just got a phone call. So when I said I'm on an online meeting, I did not get your answers. So the first question was about the costs for the license. So it's just a piece of paper. So I can be quite flexible with the cost for the license. If there's no donor or no budget for it, I can give it for 200-300 euro. That means, let's say I'm a supplier of a machine. I always have to ask at least the minimum costs for, let's say, making a briquetting press, which is 1,000 or whatever. So I want to say for the license, I'm flexible. When there's no donor and no budget, I will be very low and just put in my costs for making the manual and giving the advice. Second thing is every country has different situation with the material, and I give backstopping. If somebody comes with questions, I try to help. That's the second thing. And for the amount of palm kernels which fit into the wood chamber, I was not listening. Maybe somebody can repeat. Stop.
I think Happy said about 250 to 300 kg per load.
Okay.
Okay, thank you, Dr. Chris. Good to have you here. Kevin, you got a question about cost. I don't know if you're able to take that kind of a question yet, but do you want to speak to that at all?
You mean the capital cost?
Yeah, the cost of your 2020 kiln was the question from Saf.
The version 2, right? Yeah, so I think at this point, that's something we're discussing with our partners. So I think we instead of setting a price, I think we like to solicit what price will be reasonable for our partners. I think that might be a more productive conversation. And I think for us, a lot of it is not actually selling the hardware direct, but rather charging the per ton kind of usage fee in terms of using the reactor and the control system. So I mean, exact pricing, I mean, since we're still in prototype phase and sort of working through the instrumentation, that's something can discuss with you and just learn more about what sort of pricing is acceptable to you.
Great, thanks, Kevin. We have a question about general profitability of a charcoal business in Nigeria. There's a lot to that question. So do you want to speak briefly to that, Happy? I don't know if you can speak just kind of to maybe the scale that you found that you have to reach, or in your experience, any comments on profitability?
So I think basically this is an open-ended question. So, but what I would have to say, one is there is a huge market for the briquettes, but with briquettes you have to be really careful because your competitors, who are people who just cut down trees at the backyard, just cut it down and burn it, and at the end of the day they have a charcoal and they're selling at the market. But with briquette production you have other costs coming in. You have to, initially you may get feedstock for free, but after some time people will want you to pay for it. And also you have to be able to keep your production costs at as the lowest as possible, so that you'll be able to compete with the other products, charcoal products in the market. Because Nigeria is a big market, so of course if you do your calculations right with a large market, you should be able to be profitable. And another thing that is, it has to be in large scale, because in small scale you end up mostly just having your cost. But when you have it in large scale, that's the same reason why we've been looking for ways to go large scale, because it's more cheaper for us to have it in large scale. The same energy we will use to produce 300, 400 kg, it will be the same we will use to produce 2 tons, 3 tons. So large scale is usually more profitable than in smaller scales.
Very good. Thanks, Happy. I had a quick follow-up question related to the kiln, but in general about scaling up your business. And maybe you can take the Retort Kiln as an example. How do you find out information or learn about different technologies that can help you reach a bigger scale? Maybe for some of the newer producers who are on the call. How did you learn about the Adam Retort? Did you think about other options? And how did you get that information?
I'm always surfing the internet for information. And I'm always asking questions. Adam, Dan, sorry, you know how many questions I've asked you on on WhatsApp. I'm always asking questions. I'm always reading documents and everything. So for like the reason for the decision for the Adam Retort, it came to be the most affordable and the biggest kiln I could get at the moment, because some of the ones we saw are sophisticated and much more expensive that we could not afford as a small scale business. So these are some of the decisions and some of the things that made us come to the decisions that we took.
That's very good. Yeah, Happy, you are a go-getter. I know that. So for others as well, I'm happy to also help point you to any information that I have or suppliers, etc. So, and there may be others on the call here who have other information too. I was also curious, Happy, one of the common things that I hear from people is that some of the larger scale and maybe more efficient ways of carbonizing, some of those kiln designs are expensive. Even some of the briquetting machines are expensive. Do you have any tips on how to overcome that constraint, the cost, and finding a way to invest that, maybe if you don't have the money yourself to invest? Do you have any approaches there?
Well, I think this is one of my approaches. That's why I jump on the offer. I don't know who is here listening and has some extra funds to help us invest in our business. So I think one is we work so hard on our publicity. We also have, one of the things we did to raise our own funds was we said, okay, if we can't have investment, why can't we offer a training facility for people, and then people pay for it, and then we raise money from the trainings and consultation services we do, and then we buy some of the machines we need. And so that's how we do it, and that's how we started training people on how to make briquettes in smaller scales. And so far we have been able to train about 200 people on briquette production in small scale. So this is one way we do to raise funds. Other ways, we apply for funds everywhere that there are funds being applied for small businesses investment. We are there, we are pitching and also we look for technologies that are affordable and will give us the best output per time most of the times. So we do a lot of cost analysis to know what is best that will solve our needs at the moment. So that is it for us. I hope that was helpful.
Yeah, that was very good. Do you want to add anything there, Kevin, from the experience of Takachar?
Yeah, I mean, pretty much what was already said. Yeah.
Yeah. Good. Happy, quickly, someone has asked if they can visit. Is your facility open for visitors, or is it behind closed doors?
Yes, we are very open for visitors. We love visitors.
We have a question about the fumes from charcoal making, from carbonization. And how do people avoid those fumes? Are they dangerous? Do either of you want to speak to that?
Sure, I can take a step. So initially,
Okay.
with kilns, we had, we had some smoke, sort of the fumes. Later on, we were able to improve on among kilns to eliminate that. And in our kind of 2020 version, there isn't any kind of fumes because all of that is being utilized as energy to run the whole process. So we are getting sort of CO2 and water out. Yeah, but I mean that is a polluting kind of thing, and one of the main limitations for kind of smaller scale kind of drum or mount kilns.
Thanks, Kevin. Happy, do you want to add anything about fumes, maybe from the kilns that you have experience with?
Oh, Dan. So I usually want to avoid the most technical questions because I'm not very sure about them. But one thing I know though, with the carbonization, especially because it burns without much oxygen. So the carbon monoxide emissions is way reduced than when it's burning inefficiently with a lot of oxygen. I don't know how true that is, but I think these are some of the things that popped up during the research. And that is why when you're carbonizing in a drum and when you close it, the smoke is actually white and it has no fumes. Then I can see your eyes, so I'm so
it's okay.
It's actually not stingy to the eyes like when it's burning furiously with fumes and black soot. So these are some of the things that I just want to add. I stand to be corrected.
Happy, maybe you could just state a couple of things that you do to make sure your workers are kept safe from any inadvertent fumes.
So my workers will have to, when the carbonization process starts, they wear a mask and safety hand gloves and the moment it starts, so that we avoid burns and we also avoid inhalation of the smoke and all. And the moment it starts, actually, we don't have to stay there. We go far away because it takes a period of time before we check it.
Great. Yeah. Thanks, Happy. I think also in our experience, like Kevin was saying, when you're able to utilize those gases, right? If you're either flaring them or using them within the kiln as a heat source or even externally as a heat source, that helps to reduce the sort of danger to the workers and also the impact in general on climate, environment, and health. So in our experience, yeah, any way that you can, any measure you can take to flare those or use them in some way is much better than just the unvented, unburned emission of pyrolysis fumes, which definitely are a big threat to health and also the climate. I think, yeah, Mary and Jenga has a good comment too, that, and I think this Teddy Kinyanjui was also speaking about the capture of some of the components, at least in the vapors coming from the kiln. Some of those are actually condensable. When you cool them down, they'll produce a liquid. So we refer to that as wood vinegar or pyrolysis oil. So capturing those using a chimney or a pipe attached to the kiln is another way to clean up those fumes and vapors. Feel free, Mary or Teddy, if you want to just quickly add something there. Okay. We are actually very close to time. So I don't know, Sylvia, can we take another question or do you want to wrap up?
Let's just take one more question and then we'll wrap up after that.
Okay. Let's see. So we talked, actually, there's been a question about pyrolysis oil. I think we've talked about that a fair amount. Rate of adoption for retort kilns globally and in Nigeria. Any comments on that? I don't have good information on how many retort kilns have been constructed and are in use in Nigeria or elsewhere. Do you know, Happy, or Dr. Chris?
I don't know. I don't have that information.
Yeah. How about addressing this question quickly on the environment and the neighboring houses? Have you had any issues with that, Happy?
So the only thing we had was we had to extend the chimney. So our chimney was a little lower. So the moment we extended it high up, it solved the problem.
Okay, so the chimney, just extending that higher, was able to get any remaining fumes that may have been a nuisance to the neighbors. It would take those away.
Yes.
So great. Well, I think that's probably about time. I want to respect everyone's time and keep on schedule here. So I will thank you all, and I'll turn it over to Sylvia to finish up.
Dan?
Sorry, yes, Mary.
Yeah, sorry, I couldn't speak. I was trying to download something on the message.
Okay.
Yeah, but what I want to say is that in respect to capturing smoke, it's also good to consider what technology is simple for the people. Because what we are finding is that when we have complicated or expensive innovations, then the charcoal producers don't use them. And so, especially what has been mentioned as just fixing a pipe or a chimney, and then this chimney, you have a container where the smoke flows through the chimney, it cools down, liquidifies, and then you collect it. And that way you reduce releasing it into the air and to the people also. And I have attached
Very
a
good.
practical guide, very simple guide that shows how you can even improve the traditional kilns that are being used in Africa, the earth kiln. It can be improved and you can get mass efficiency from 15% to about 22%. And at $55 only, you know, or
Very nice.
it's nothing, yeah. So simple, but you get some benefit. Thanks so much.
Thank you so much, Mary.
Thank you.
Thank you.
Mary.
Yeah, thanks for sharing.
Thanks.
All
Mary.
right, Sylvia, over to you.
Okay, thank you all our speakers and all of you who jumped in on the conversation. I think this was a great discussion, and I know a lot of you are looking forward to getting the recording to review some of the more technical aspects, which of course we kind of race through and will want to be studied by many of you. Dan, especially thanks to you for moderating a great conversation. Kevin and Happy, we really appreciate all your contributions. Just wanted to give you a heads up. We have some other webinars coming up. Like I said, we're continuing this series throughout this year and next year, just to keep people aware of the issues and developments in charcoal and making charcoal a more sustainable fuel. Our next one is going to be focused on the global trade in charcoal, which I think a lot of you will be interested in. If there's any topics on this list that you think are missing, or there are topics that are not on the list that you think we should be delving into, just shoot me an email at sherzog@charcoalproject.org. We're happy to consider, you know, what people want to hear more about. And with that, I'm going to wrap things up. Again, thank you. We'll be sharing all this information with you directly via email in about a week or so. I'm gonna stop the recording now, and thanks again for your time.